تمام. في مشكلة. Good morning, everyone. Can you hear my voice? Good morning.
Good morning, Dr.
Is it okay now? Okay. تمام. Good morning. Today is our second lecture or our second day for our workshop. We yesterday enjoyed very nice 5 lectures or 4 lectures, to be honest, because the opening I can't count it as a lecture. But yesterday we had very nice presentations by Professor Sharif Murad, Professor Majid Hassan, Professor Piero Francesco, Professor Casticadellis. Today we will have another 5 interesting lectures. Dr. Masoud is going to start, and it will be followed by Dr. Ashraf Ayub and Dr. Ahmad Omar. These 3 lectures is going to cover the first acts of our workshop. The first 2 lectures is going to talk about the Zoser pyramid or the state pyramid in Egypt. The third one is going to cover Cairo Citadel, and we will end up by 2 new talks in basic sciences and engineering. One is going to be covered by Professor Alex Chang, who is the editor of Engineering Analysis of Boundary Elements, and Professor Edward Kansa, who is the founder of Kansa method, which is a way to solve the partial differential equations in the differential form. I'm going to start this today with a lecture from Dr. Masoud. Dr. Masoud is working with Professor Piero Francesco in Brighton team. He is very expert, I believe, in modern engineering. I have seen his work. He's very impressive, to be honest, in health monitoring, dynamics, in modeling soil, superstructure. I believe we will enjoy a lot about his lecture. He's talking about the use of VIBA to control Zoser pyramid. Dr. Masoud, you can unmute yourself now, and you can share your screen and start talk within the coming 1 minute or something like that.
Hello, Ahmed. Very nice to meet you. Everyone, can you hear me? No? Can you hear me? Hello?
Dr. Masoud, I can't hear you.
Oh, okay, brilliant. Thank you so much.
Okay. اسأل عبد الرحمن إيهاب كده في مشكلة في الفويس. أكونكت على طول في اليوم. دكتور مسعود. دكتور مسعود. دكتور مسعود أنا مش سامعينك، في حاجة عندك في الساوند سيستم. You have something in the sound system, I believe.
Really? So I will speak loudly.
The microphone, Dr. Masoud.
I think the microphone is there.
Do you hear my? Just type,
loudly.
Dr. Masoud. Just type. If you can hear me, just type in the chat.
It's very strange. Okay. Right.
Can you hear me, Dr. Masoud? I can see your screen. I can see your screen. I can see your screen, but
Okay. So can you hear me right now?
I can
Yes or
see
no?
your screen, but I can't hear your voice.
Oh, I see. What about now? No?
Oh,
Do audio settings. Speaker.
page.
Can you hear me right now?
Okay, I can hear you now.
Okay, brilliant.
Okay,
Okay,
share
excellent.
your screen. Share your screen. Okay, I'm sorry for this interruption.
So that's fine. That's fine. So, hello everyone. Today I'm talking about non-invasive vibrating control of the Zoser pyramid. We are a team of two UK universities and Cairo University in Egypt. And this project is supported by AHRC. And in this lecture, I'm talking about our work at the University of Brighton. My name is Masoud Shadlou, and please follow me in the next 20 or 30 minutes. Okay. So first, I will talk about non-invasive and invasive vibrating controls. If you have already attended in this workshop, you may wonder that my colleague Piero has already explained about the difference between two. So I will just talk a little bit about it. And then I will talk about structure, soil structure interaction mechanism, which is related to the vibrating control design. So I will talk about a little bit about that part. And the next part will be about the statement of the problem for this project that we are dealing with. And then I will talk about computational challenges, about the reduced order method that we have developed for this project, and design cases, and we will discuss about the result at the end. So in 1992, there was an earthquake in Egypt. So as a result, we may see that some of the old structural heritage in the world was affected by the earthquake. So some of them were closed for a long time. As you see in the left side shows that the number of earthquakes happened, around the Zoser pyramid. So as a result, there will be huge damage for a huge demand for protecting Zoser pyramid for the future earthquake. To explain about the difference between non-invasive and invasive vibrating control, I would say that we know about several techniques for strengthening like the buildings to just protect it for the next earthquake, or we may use the base isolation or dampers and etc. So these techniques, these vibrating control techniques may be useful for conventional buildings, but it may not be useful for the unusual structure like the pyramid that I'm going to talk about. So we may think to use other techniques in this case. One technique might be using meta materials or meta barriers. But these meta materials or meta barriers may be useful just only for railways or, for example, glass and etc. And it has not been proven to be useful for earthquake mitigation, etc. But another technique, which is highlighted in this research or in this lecture, was suggested by my colleague at the University of Brighton. So, and this is called vibrating barrier or VIBA. So the vibrating barrier or VIBA works under the concept of structure-soil structure interaction. So in the next slide, I will present more details about this topic. Just assume that we live in a metropolitan. So it's a dense, urban area. So all of the buildings are located next to each other. So when an earthquake happens, for example, the bottom shows the London, and this is the Shard and the London Bridge, and etc. Just assume that when earthquake happens, then one building will vibrate, and another building also will vibrate. But as the vibration characteristic of each buildings will be different, the one building, for example, that building, will be affected by the vibration of this building. So this phenomenon called structure-soil structure interaction. So as a result, we expect to see that when earthquake happens, these structure-soil structure interaction would be beneficial or detrimental according to the vibration characteristics of buildings. But the point is there, WIBA is getting more benefits of the structure-soil structure interaction. As a result, it's like that we design a building, for example, or we design a system next to the target buildings to just make sure that it will absorb more energy, or it will vibrate to reduce the vibration of the next building. So this building, this target building can be one building or can be a cluster of buildings. And the cluster of buildings has already been researched, at the University of Brighton by my senior colleagues. But the point is there, when we want to design the WIBA, we may need to use several techniques, several numerical techniques, like, for example, finite element model or boundary element model, or we may use the simplified 1D model. But when we are going to deal with design of these things, we have got several challenges. And the challenges are related to the number of variables that we deal with. For example, these variables might come from the structure, like the materials properties or the nature of the loads, several things. But at the end, because we are going to make sure that our design is robust and we are sure about our design for the future earthquake, we need to carry out, Monte Carlo simulation, parametric studies, and multi-level optimization techniques, etc. So design is very challenging topic for this specific vibrating control concept. Now let's talk further why it's very complicated. For example, in this lecture, I'm talking about somehow a simplified geometry of the pyramid. So we have already modeled the real geometry of the pyramid, but in this lecture, this simplified model is explained. So how's that one? We have tried to model the pyramid as a stepped pyramid. So, but the point is there, the natural frequency and the mode shape and etc. will be exactly the same as the real geometry. Assume that we put this pyramid on the bedrock, and when we apply the loading, we will see that the transfer function of the pyramid alone would be this shape. So, for example, the natural frequency will be about 14 Hz. When we put it on over the soil, we rest it on the soil, according to these properties of the soil that we received from Cairo team, we see that the natural frequency will be around 10 Hz. But another important point about this system would be the role of the second mode into the response. As you see that, for example, the first mode will be 10 Hz and the second mode will be about 17 Hz. And we expect to see that the second mode will have a bit higher contribution into the response. So we are dealing with an unusual structure, not, for example, the usual structure that we see that, for example, first mode has a very high, participation effect into the response and etc. So we expect to see that first, pyramid is not a rigid base structure. So it means that conventional, for example, 1D modeling technique may not be useful. What is conventional 1D modeling technique? For example, using the spring for modeling the soil or using the spring mass for modeling the pyramid. So using a spring and mass and damper and etc. for the pyramid may not be accurate because we are dealing with the two modes of the vibration, and also we are dealing with the uh, flexible based system, and it's not a rigid based structure. So we need to deal with this kind of the challenges when we are going to design the YBA. As we know that we are dealing with a large degree of freedom, so it creates a lot of challenges. Now let's look at it further. For conventional design, as a structure engineer or geotechnical engineer, we normally create a finite element model, and then we try to change the variables, and change the design variables, and then we will do the analysis, and then we check it that it's okay or no. And if it is not, we change the, this kind of design variable. So this is like in, an iterative process. So we check it, we set it, check it, and then we set it, and etc. So this is conventional design. This will be really complicated, time consuming, when we are dealing with the probability of inputs. So in this case, the analysis will be much complicated. So we need to do thousands of analysis for specifically designing the YBA to just make sure that it will be robust and valid for different scenarios of loading and etc. That will be really time consuming. Why it's time consuming? The point is there. When we are modeling the pyramid and the soil, we are dealing with like millions degree of freedoms. So as a result, one analysis will take at least, for example, in the time domain analysis will be at least 2 hours for a normal 20-second airstrip. So designing such a system with these kind of, variables and probabilities and etc. may need for us to design, to create a new type of model, or reduce the scale, or reduce the degree of freedom of this structure. What is this? For example, just we have got the second order differential equation for a structure. We are going to make sure that we create a replica for that structure to make sure that it will have some important properties. What are these important properties? It means that the target structure, and when we compare the target structure and original structure, we must be sure that we are capturing the, the dynamics of the system. We must be sure that we are producing the physical, reproducing the physical behavior. It must have, they must have the same physical behavior. And we must retain the parametric dependencies of these systems. And as well as the most important part is efficient method, because we are dealing with a repeated analysis. So it means that we need to create a reduced order model of this system with this large degree of freedom to make sure that we will have the same response. You may think that, okay, for such a system, we may use the homogenization technique, and we create an RVE and do the integration of the stress, the strain, and etc. That's a really cool thing, but it may not be suitable for this project because we are dealing with thousands of analysis. We need to reduce these skills to much lower, and also to make sure that analysis will be quick. So on the other hand, we cannot use the spring mass and damper and etc. for modeling the structure. So this will be really complicated. But what will be our methodology for reduced order method and etc.? So I discussed about the conventional or old method, but now I'm talking about a new one. So old is not always gold. Sometimes the new one is really gold. So I'm talking about it specifically. Let's say that at the beginning, instead of carrying out thousands of analyses with the finite element model, we just carry out 2 or 3 finite element models. And at the end, we save the result into our database, and we take it out for the design process whenever we want. So for example, we save all of the stress components, strain components, displacement, velocity, acceleration, and whenever we want it, then we will take it from our database and we'll use it, because we will call those components as an unchanged matrix or unchanged vectors. So whenever we want, we will use it. I will explain it in the next slide how it's happened, but please follow me here first. So then we'll go to the design process, and then we will have this loop for the design. But at the end, we will be happy because the process will be straightforward and the accuracy also will be high. But for the design and optimization process, we are dealing with the several variables, because the function that we generate will be a multi-function or multi-variable function. So we are using Nelomid simplex method. So so this is the concept of this is the design process for the VIBA. This part that I talked about it about several finite element model limited number. So we used it. It's called the reduced order method. So the reduced order method, we only carried out this limited number of analysis, and then we will use the data. And in this case, we are able to design according to the probability of input, and we can get the probability of output and use the integration of et cetera, that you may already know about it. So to get the final design. But what are these three finite element models? Let's look at this slide. First of all, we carried out the finite element model with the full degree of freedoms. We apply the earthquake on the bedrock, or a motion on the bedrock. And then we obtain the response of the system. For the next finite element model, we will carry out the loading on the rigid excavation, and we find the response of the system. This response, just I showed the displacement. It can be a stress, strain, velocity, acceleration, etc. And we have got another structure related, to the VIBA. So we will try to make the relation between all of them through this equation. So this equation will try to consider all of the components for the design. For example, as I said before, this UP component can be stress, strain, displacement, velocity, and acceleration. And all of them will be considered into this equation. We can go and design the one which is already considered in V omega, which is already comes from here. So we have got this reduced order method. Let's look at the input parameters and its variabilities. First of all, for this project, we have several inputs or variables. First of all, first of them comes from the variability of seismic activity at the Zoser pyramid. This seismic activity at the Zoser pyramid we may have some sources like the angle of incidence of, for the earthquake, distance of the earthquake, moment magnitude of the, and stress drop. So all of these parameters can be considered as a vector inside a general variable. We call it as an alpha. So as a result, we expect to have a probability of each of these inputs. So let's say, for example, for the distance, we will have some probability, magnitude, and etc. So we will be able to consider all of them into the seismological model, and accordingly, we are able to generate the earthquake at the bedrock. But another variability that we are dealing with this in the project would be about geometry and the distance between VIBA foundation and pyramid. So we are dealing, as you see, that we are dealing with a large number of variables, and we need to consider all of them into our design. But in this specific lecture, I am going to simplify this design process, and we take a look on a variability of earthquake into our design. So for example, we just considered 3 cases of Viva foundation, and they are located at the same distance to the pyramid. And we generated the PSD function of the earthquake, Cairo earthquake at the bedrock, as well as, for example, showing that this is one of the time series. So we are going to use these simplified variabilities into the design concept. You may see that when we do the, so I told you about the alpha or variability of the seismological parameters in the past. Now we are dealing with another kind of the variability, like for example, VIBA design option. So it means that we have got alpha and beta in our design process. Alpha comes from the earthquake and beta comes from the VIBA. So at the end, for example, when we have got displacement, let's say, we displacement in the frequency domain will be as a function of beta, which we know that because it comes from the VIBA, times the UG omega. And this UG omega, which comes from the earthquake, will have another variable comes, let's say, alpha. So we expect to see that acceleration, displacement, etc., will be a function of both alpha and beta. So it's a very complicated, as you may see, that this system. But take a look on this example of the analysis that we carried out for that specific simplified pyramid, step pyramid. So we see that if we expect to see that the transfer function for the pyramid for the range of 18 to 12 hertz, for example, for without the VIBA will be like that. When we design the VIBA, the transfer function will reduce a lot. So at the end, we expect to see that this area, for this specific area, we will absorb the energy, or the VIBA will work to reduce the vibration of the target structure like pyramid. For example, the right side, we show that for different cases, when we consider one earthquake or one realization, we see that how acceleration at the top of the pyramid and one meso's stress at one specific element reduced. For example, as you see that almost 20% reduction we expect on the one meso's stress on the pyramid, as you see, or we expect to see this kind of reduction on acceleration. So these are some of the results related to that one. But let's take a look on one meso's stress and comparing the original structure or original pyramid with one that we use only a rigid excavation. So assume that at the bottom, we don't have any VIBA, just only excavation. And we see that does this excavation isolate the structure during the earthquake? As we compare it, the one meso's stress, you will see that this rigid excavation, even very close to the pyramid, is not able to isolate the structure or reduce the response of the system. While when we use the VIBA, we expect to see this kind of the reduction for all 3 cases. Even when we put the VIBA on just one side, we expect to see the reduction in the whole system. So this slide shows that the VIBA clearly works, and we expect that it reduces the earthquake damage on the building, because as you see that here we expect very high one meso's stress example, when we use the WIBA, this area that's already damaged in the previous earthquake or in the past, we expect to see that, wall mesoscale stress reduce a lot. So if we take a look on a cross section, we will see that, for example, when we don't use the WIBA, we expect to have this one mesos around, let's say, this number 677. But when we use the WIBA for different cases, we see that at the core and at the side, the one mesos stress reduced considerably. So this means that even in the core of this, in the pyramid, in the center of the pyramid, we will see the reduction in one mesos stress. We carried out the Monte Carlo simulation in this lecture for this specific lecture and accompanying, the paper presented at the contact conference. We carried out just only 30 realizations or number of earthquakes. But in our final model, we have used thousands of analyses. So let's look at this one specifically. It's talk about the cumulative average. As you see that when we don't use the WIBA, we expect to see that acceleration will be about this value, like 11 meter 11 meter per second something. And when we use the WIBA, we expect to see this kind of the reduction. It's about 20 to 25% reduction in terms of acceleration. And when we compare it with the one mesos stress, we expect to see that it will be the same. We will see the reduction on the one mesos stress. And even it is clear that case one will have a higher reduction on the cumulative average of one mesos stress than, for example, case 3. So this means that even changing the shape and size, those properties and the distance will definitely affect the design concept. So to just conclude my presentation today, we have carried out Monte Carlo simulation. We generated the reduced order method for this specific structure, and we have seen that the peak acceleration has reduced about more than 20%, and one mesos stress reduced around 24%. So we have developed a method, a reduced order method, and we have presented this research in one conference, and we are writing up now a paper for Nature, scientific report in Nature, and we will submit it maybe next week. Thank you very much. Thank you.
Thank you, Dr. Masoud, for this nice presentation. Before I go through any comment or anything regarding questions or something like that, I would like to welcome Professor Abed Saleh, who is a president of the Manhoor University. He is with us in the chat room, and on this presentation, he is a great guy and he's a great leader, to be honest, for his university. I welcome him a lot, and this is our privilege to have him with us. Now, thank you again, Dr. Masoud, and we have actually plenty of time to ask a question. If you want to ask a question regarding Dr. Masoud talk, you can just directly unmute yourself and ask the question. Till now, I think everybody is pleased with your talk. Anyway, I will personally, I will ask you a question. I'm very happy, actually. I'm very happy about your talk and about the WIBA. And I especially, I would like to ask Piero for this nice idea. But I have only one main problem with fiber is the amount of mass we use. Is it practical? This is my question. So sometimes you use something like 0.8 of the structural weight of the building you are preserving or something like that. So is this practical?
You know, or my senior colleagues at the University of Brighton has worked on this topic for a long time, you know, and they have considered, you know, several, you know, technique to just make sure that design will be suitable for, you know, to just build in practice. For example, they developed one called the inerter, you know, and by using this inerter, we are able to reduce the mass. So they have already did the research on this topic. So I would say that it would be practical, you know, because in this case, even we are able to reduce the mass and we increase the functionality of the Wi-Fi. You are right that we may use the, you know, large mass for this system to work and reduce the earthquake, but I would say that using inerter will reduce the mass, and we expect that when we reduce the mass, we expect more practical application for this project. But apart from it, I would say that even in our complicated design that we are dealing with right now, we have, you know, defined a very high width foundation with lower embedment depths. So in this case, we found that we
need to ask. If you look about the placement of the fiber itself around the structure itself.
Hello, good morning.
Hello.
Hello.
Hello, we
Can
can
you hear
hear
me?
you.
Do you hear me?
We can hear you.
Oh, yes.
Okay. I would like to thank Dr. Yusuf Rashid to give us the chance to attend this workshop. I have two questions. The first one, maybe I attend late. I would like to ask about the trench, the dimension of the trench, and how can we construct this trench, especially when it is empty. Can we use the sheet pile wall or something like this? And the second question, how did you simulate the ground motion? I mean the acceleration and the direction of this acceleration time history using, I didn't catch it. Thank you.
Okay. Thank you very much for this question. I will go back to just specifically talking about first part, about it, for example, the dimension of this excavation, etc. Yeah, this excavation can be like other buildings. You know, when we carried out the excavation, we create the retaining walls and etc. You know, it will be a very strong foundation because we expect to see that this foundation will be rigid enough. So we are dealing with this kind of the design for specifically for the foundation. But for the earthquake input, if you okay, here I talked about, you know, the variability of seismic activity at the Zoser period. So we are dealing with several variables like angle of incidence, distance, moment magnitude, stress drop, and etc. As a result, each of them will have a probability. So we will consider all of the probability in this Bohr method, and then we generate the PSD of the bedrock motion, and so we generated, you know, thousands of records. So this is the specifically for the second part of your question. I hope I answered.
I forgot to welcome Dr.
Thank you.
Yasser Al-Hakim. He is my old colleague and my friend, to be honest. Welcome, Dr. Yasser. Long time I haven't seen you, to be honest.
Thank you.
Do we have other questions? I don't think so. So thank you, Dr. Masoud. And we will come back in 1 hour time because Dr. Ashraf Ayub he will have a presentation on earthquake damage mitigation of Sahara Pyramid through vibrating barriers in numerical study with Muhammad. So this will be after 1 hour from now exactly. We'll have our cup of coffee or something like that now, because I haven't have my coffee until now. I just worry about organizing this stuff. So after 1 hour, we have break for 1 hour now, then we will come back again. I will say break for 1 hour because we have different time zones. So after 1 hour, whatever your time is, okay? So see you in 1 hour time. Thank you everybody.
Thank you.
Thank you.
Right. Thank you.